Hello College Algebra student. This video is for chapter 6.1 part 4. We'll finish up with going details into the continuous exponential model. So this exponential model can be used to model something that grow or decay continuously. That means there is not a particular b that you multiply. So and then it depends on using e as the base. And so the way you do it was because e is 1 plus 1 over n to the n, 1 over n to the power n. So this would be this is a kind of similar to the b that we're talking about. So when we write the model, the growth or decay model for continuous exponential growth or decay is a amount after time t is initial a, again initial, times instead of b it would be e to the rt. So all of the exponential function has the same base e, but the only difference is the r. R is the continuous growth or decay rate. So notice they use this word that attached to it. It's different from the growth rate or decay rate that we talked about earlier. So earlier our r would be 1 plus r is equal to b for growth, right? And also 1 minus r is equal to b for decay. So that is just a growth rate and a decay rate. But this is continuous growth rate. So that although we use the same notation, but like same symbols, but it's actually different. And also you can see that you do not need to add 1. You just put r over there. It's especially true for decay also. You don't have to do minus. So it already tells you what is remaining. Okay, which is very nice because earlier when we do depreciation or decrease, we have to do 1 minus to see what is left over. So again, how do I model it? For growth, r is positive. You use the sign of r to tell you if it's growing or decaying. If r is negative, then it is decay. Okay, so for example, there's two exponential functions that use e that model continuous growth and decay. So this is a negative r. So I know it is representing continuous decay. This is, although it's very small, but this is a rate that is growing. So it is positive. So it is positive. It is a continuous growth. And in a business application where we are growing the money continuously, then instead of P1 plus R over N, that big formula, we would use PA is equal to the present value, E to the power RT. So it's very clean. And it would model money growing continuously. That means the bank is going to give you money and it would compound continuously. So this could be like kind of treat as the top dollar that you will get if you use that money to invest for anything at a certain rate. Okay. So again, we'll go over this. P is the principal, just like before. Present value. R is the growth rate. Now, this growth rate, when you are doing compound interest, is the nominal rate or the continuous growth rate. Okay. Only when you're doing interest. Okay. Also known as nominal rate. T is the time. In general, it's a year. Okay, so let's do an example. Someone put $5,000 in an account, and this bank is very funny. It can give you a compound continuously for a 10% nominal rate. So all we need to do, and for 3 years, so we would need P equal to 5,000. So just write down what you have. R is 0.1 and T is 3. So we know our model is 8 of 3 is equal to P, 5,000, e to the power r times 3, r times t, 0.1 times 3. That means 0.3, right? So we just write it out. 5,000 e to the power 0.3. So put in the calculator, you need to know where your e is. 5,000 times e to the power 0.3 for 3 years. 6749.29 up to census. Okay, so after 3 years, that's what you have. So it would be like the maximum that you can get out of 10%. Example 2 is continuous decay. Okay, so continuous decay. So and continuous, and which is used to model radioactive decay. So this radioactive element decrease 8% per day, but continuously, not just per year or per day, actually continuously 8%. So which is different from 8% per day. 8% per day would be B equal to 0.9, right? So in the AB, Y equal to ABX model, not continuous would be 1 minus 0.08. But in a e to the R, A e to the RT model, your R is just 0.8. Oh, negative 0.8 for decay, negative 0.08. You don't have to say 0.92. So how much will be after 10 days? So we will say A is equal to initial is 50, e to the 0.08, but negative because it's continuous, times t. So now 10 days, 8 of 10 would be 50 e to the negative 0.08 times 10. So put in the calculator 50 times e to the negative 0.08 times 10. So I get 22.4664. This is not money, but it's just radioactive. So we do 4 decimal places, right? So continuous growth has this benefit of having the same base, all of them, so you can compare their growth rate, and you can just look at the sign of R to know if it's positive or negative. To know whether positive model growth, negative models decay. So here I'm going to talk about, I mentioned this. This model is a discrete model or the ABX model where your exponent only have x, okay, nothing else, just x. For using E as the base, your exponent would have R and x, where growth would be B greater than 1 or R greater than 0. Decay would be for B being a fraction or R is less than 0. Okay. And remember to recognize what is given. If they tell you growth or decay rate but no continuous, you would use B model. You use the ABX model and you would add B is equal to 1 plus the growth rate, or B is equal to 1 minus the decay rate, right? So if they just depends on what they give you. If they give you a continuous growth or decay rate or compounding continuous rate, then you use y equal to a e to the rx model. So that is the main difference. Okay, so that's all of 6.1. It's quite long.